All around us right now, machines are learning to think. And that sounds like something straight out of a movie, but it is the science fact that powers so much of our modern world. In this explainer, we are going to pull back the curtain and demystify one of the most powerful technologies ever created, deep learning.
I mean, just think about it for a second. How does your phone unlock just by looking at your face? Or how does a streaming service know exactly the movie you're in the mood for tonight? It's not magic, not really, but it is an absolutely incredible process happening behind the scenes, and we're about to break down exactly how it all works. The secret ingredient to all of this, it's a revolutionary field of artificial intelligence called deep learning. And it's basically the invisible engine running inside all the smart tech we use every single day.
So, where does deep learning fit into the big picture? Well, think of it like this. You've got artificial intelligence, or AI, which is the whole universe of making machines smart. Inside that universe is the galaxy of machine learning, which is all about letting computers learn from data. And right at the heart of that galaxy is deep learning. It's this supercharged star system that uses complex structures inspired by, you guessed it, the human brain itself.
Okay, but that begs a pretty big question, right? If these ideas have been around for a while, why is deep learning completely exploding right now? What changed? What created this perfect environment for a tech revolution?
Well, it really came down to a perfect storm of three things happening at once. First, you need fuel, and starting around 2005, social media gave us this unimaginable flood of data, pictures, videos, text, you name it. Second, you need the pipeline, so big data tech was born to actually manage and organize all that info. And finally, you need the engine. And it turns out that powerful GPUs, the graphics cards originally made for video games, were the perfect high-speed hardware to run these huge models.
And this, right here, is probably the single most important reason for its success. Check out this graph. Traditional learning models, that blue line, they kind of hit a wall. You can give them more data, but eventually they just plateau. But deep learning models, that's the red line, they are different. They are absolutely data hungry. The more you feed them, the smarter and more accurate they get.
So, how do we actually go about building one of these learning machines? Well, the core idea is kind of simple, but it's incredibly powerful. We try to mimic the structure of our own brains by creating something called an artificial neural network.
All right, let's zoom all the way in. The fundamental building block, the single little atom of this artificial brain, is called a perceptron. Just think of it as one artificial neuron. Its job is pretty simple. It takes in some information, decides how important each piece is, and then makes a basic call.
Now, this might look a little technical, but trust me, the idea is super straightforward. This one neuron, this perceptron, is just a little decision maker. It takes in some info, we call those inputs. Then it decides how important each bit of info is using a weight. Finally, it just adds it all up and uses something called an activation function to make a simple yes or no decision.
So to put it all together in one go, the neuron gets information, it weighs how important that information is, it adds it all up, and then a final gatekeeper, that activation function, decides if the signal is strong enough to pass on as a yes or a no. That's it. That is the fundamental decision at the very heart of the entire network.
Okay, a single neuron is a great start, but it has one big problem. It can only solve really simple problems, things that can be split with a single straight line. But the real world? It's way more complicated than that. So what's the solution? Well, we don't just use one neuron, we use millions of them, and we stack them in layers. And by creating these deep stacks of neurons, we give the machine the ability to understand unbelievably complex patterns. This, right here, is where the deep and deep learning gets its name.
Okay, this is where things get really, really cool. We've built the structure of the brain, but how do we get it to actually learn? Well, the secret is all about making mistakes, measuring how bad those mistakes are, and then, little by little, getting better.
I mean, think about it. The whole system runs on those weights we talked about. But how on earth does the network figure out the right numbers for thousands or even millions of these weights? How does it actually get smarter over time? The process starts by admitting it's wrong. To do that, we use something called a loss function. You can think of it as a scorekeeper for failure. It calculates just how big the gap is between the network's guess and the actual correct answer. A big gap means a high loss score. The entire goal of training is to get that loss score as close to zero as humanly possible.
And the way it finds that lowest score is just brilliant. Imagine the loss is a giant foggy valley, and our network is a hiker trying to find the very bottom. The hiker is blindfolded, but they can feel the slope of the ground right under their feet. So what do? They take one step in whatever direction feels steepest going down. Then they stop, feel the slope again, and take another step down. This step-by-step process of feeling the slope and heading downhill is called gradient descent. So after our hiker takes a step, they know how wrong they were. Now the network has to actually learn from that mistake. It sends that error signal, that you were this wrong message, all the way backward through the entire network, from the very end to the very beginning. And at each layer, it tells every single neuron how it messed up, and it adjusts its weights just a tiny, tiny bit. This whole feedback loop is called back propagation. Now, our hiker can choose different ways to get down the valley. These strategies are called optimizers. They could check the slope of the entire valley before every single step. That's really slow, but super stable. Or they could just take a wild guess based on one tiny patch of ground. That's way faster, but also kind of chaotic. But the most popular method is a happy medium, looking at a small batch of ground before each step. It's efficient, it's effective, and it's pretty much the best of both worlds. All right, so we've got the brain structure, we've got the learning process. Now let's put it all together and look at one of the most mind-blowing applications of this stuff, teaching a computer how to actually see. To teach a computer to see, we use a special kind of network called a convolutional neural network, or a CNN. And what's so amazing about it is that its design is directly inspired by how the visual cortex in our own brains works, by breaking down images into simple little features, like edges and colors and patterns.
So how does a CNN actually see? Well, imagine it slides a tiny magnifying glass called a filter across the entire image. This filter is like a little detective that's been trained to spot just one thing, maybe a vertical line or a curve or a patch of red. Every time it finds a match, it makes a note on a new map. And by doing this thousands of times with thousands of different detectives, the network builds this incredibly rich blueprint of every single feature in the image.
And here it is, the whole journey from start to finish. An image goes in on the left. It passes through layer after layer, with the first layers spotting simple stuff like lines and curves, and the later layers combining those into complex things like ears and legs and snouts. Finally, all that visual evidence gets fed into a decision-making part of the network that makes the final call. Is it a horse or is it a zebra? This is literally how a machine learns to recognize what it's seeing. So, we've built machines that can learn from their own mistakes, and now they can see and actually interpret the world around them. It really just leaves us with one